number 2, and we are here to present supercapacitor equivalent circuit analysis. We are Fer, Beto, Homero, Alex, and Michelle.
To begin, first we have to know about concepts like capacitance, RC circuits, current, and electric field. And we will focus on RC circuits that contains resistance and capacitance.
We have here a circuit diagram which has several elements. R representing the resistance, C the capacitor, A and B a switch, and epsilon power battery. In this circuit we have two possible cases. When the switch is located in B, our loop doesn't include the battery, so we can tell this is discharging. On the other hand, when the switch is located in A, the battery is included in the loop, so it's charging.
The experiment we did for this challenge was a homemade capacitor. This capacitor was made with two plates modeled with aluminum. Each plate has the same area. And in every corner of the capacitor, we put a little piece of cardboard. And this cardboard was determined as the distance that the two plates was going to have. First, we measure with a multimeter the energy that our battery, the energy source has. And then we connect our capacitor to the energy source and wait 5 minutes until the capacitor acquires some energy. After this time, we disconnect the capacitor from the energy source and we measure again with the multimeter, touching each plate respectively in order to observe how much energy this capacitor had acquired from the energy source. After having these measurements, we proceed to calculate the respective things. As we know, the equation that models an RC circuit is established by the Kirchhoff's loop law. Since we don't have any junction in our model, we can assume that the charge is going to pass through each component of the circuit, which are the resistance, the resistor, and the capacitor. Well, we know that this differential equation is stated by R times Q prime plus Q over C equals E. But in this case, we decided to put it in standard form because it is an easier way to understand it and to solve it for us.
Well, the calculations in the experiment values, first we have to say that we only do the calculations of the small capacitor that we did. And first we do the capacitance, that was this, those 2.21 times 10 over 12, minus 12. And we take the resistance of a LED, that was this, 0.005 amperes. And the initial value we take was the battery of 9 volts and a time. And our differential of potential, we determined that was the same as the battery. First, we do the maximum charging time, tau. Then we do the maximum charge, that was 1.98 times 10 to the minus 5. And the maximum current, that was 5 times 10 to the minus 3 amperes.
Now, as we can see in our experimental values, in our calculations, almost all the functions that have time on it, the result will be 0, and that's because our resistance value, that is here, and our capacitance value, that is 2.21 times 10 to the minus 17, are very, very low, and consequently, our value of tau will also be low.
True.
Instead of doing the analysis of the second capacitor, we better choose as a team, do the calculation, the same calculations for ideal values, which are the ones that are here, which is capacitance of 5 times 10 to the minus 5 farads, resistance of 8 times 10 to the 5 ohms time, which is the same, the ideal time, 10 seconds. Tau, we obtain here the tau, which is 4 seconds, and the electromotive force, which is 9 volts. And we obtain also maximum charge, which is Qmax, that is 45 microcoulombs.
For the case of maximum current, we take initial value of time when it's 0 that says that maximum current is the maximum current intensity a resistance can adopt. As we can see, it only depends on the voltage and on the resistance, and we have a value of 11.25 microamperes. For the types of time-dependent charging and time of discharge, we notice that there are functions in terms of t. For the time-dependent charging case, we got a value of 4.13 times 10 to the minus 5 microcoulombs, and the time of discharge when time is equal to 10 seconds is 9.23 times 10 to the minus 7 amperes. Last but not least, we have time-dependent current, that is the value of the current in a certain point of time, of course 10 seconds. We have a value of 9.23 times 10 to the minus 7 amperes. As we can see, these are more considerable values than in our experimental case.
Well, we use MATLAB because we were working on with this software all over the course, and because it is a very powerful tool that can help us to solve any kind of problems. The first numerical method we are going to present is the Euler's method. This method is the easier one that can help us to solve a differential equation with an initial value problem. In this case, an initial value problem is t plus 0. And this method helps us to predict the value of an independent variable, of a dependent variable with the derivative with respect to an dependent variable. In this case, we want to obtain the value of q with respect to t. So this plot is with our experimental values we obtained in the first part. And as we can see, the charge is very, very low in a very short time. This is due to the fact that our values that we obtain are very, very lower than 0. So this is the plot we obtained.
We also use a second method, which is OD45. In this, with this method, we also use the experimental values. With this function, it's a MATLAB function, so we have that its span is interval of time, which is a vector 0 to 10. We have the initial value Q0 equals 0, which we use it for a particular solution. And also we call RC1, which is our function we create, which answers the OD here with our values. And as we can see, the graphic is also like the one before, and well, the behavior is almost the same. And that's
For the ideal values,
Now, as my partner said, for the DI values, a paragraph is shown where the capacitor charge rises not so quickly as it does with the experimental values, and it tends, it approaches its full charge while time tends to infinity, and this is shown in both methods. But ODE method is a more precisely method. That's because it rises exponentially, and the Euler's method depends on the distance between the points.
Here we compare the plots of charging a capacitor, the charge, and the current. And here we can see that the charge, when the time is increasing, the charge goes to the maximum value. And here in the current charging, we see that the current becomes from the maximum value and goes to the minimum value, and the time increases and goes to the infinity.
for a discharging capacitor, we have, of course, the values of the Q and the values of the current. In this case, we can see that, of course, since in our circuit diagram, the switch is located in V, of course, through time, the charge will be decreasing. That's why our path follows a decreasing path. And indeed, in this case, we have a very interesting plot. This is why that in the first element of the equation of current, we have a negative sign. That's why our path seems to be increasing, but if we see the parameters, it comes from 1.2 to 0. So at first sight, it may look that it's increasing, but indeed is decreasing too.
Now, supercapacitor. Supercapacitor is identified from a normal one because it will have a much bigger area and the distance between the plates will be smaller. And it also has to be noted that the charge and discharge time will be more durable in a supercapacitor. And that's exactly what we're going to do. We're going to make a plate with much bigger area and cut the distance between the plates so the separator will work in a different way, more efficiently. And that's how we're going to make a supercapacitor.
Also, we want to talk about the opportunity areas. First, I will talk about MATLAB. MATLAB don't let us take a lot of decimals, and this is a disadvantage, because we are working with a pretty little small quantities, so it doesn't give us the result we want, for example, in the graphics. Also, with MATLAB, we know how to use MATLAB, but sometimes it's really difficult to put into words in the program what we want to explain. Also, better materials in the physical experiment. We can use better materials, and also, or in experience, don't let us take the right measurement, like we said here. Well, we have like an exact values. Also, improve the results. We understand. We take a lot of time making a pretty good analysis of the data we obtain, physically, theoretically, and also, well, with the ideal values.
And in conclusion, we think that we do well the challenge, and these kind of topics are essential in our lives because the supercapacitors and capacitors are in our daily day in phones, laptops, and most of the electronics. And also these give us like the pillars or the fundamental concepts to our professional career and our professional life. Thank you.
And that's all. Thank you.
Thank you very much.
Thank you so much.
And you took around, was that like 12 minutes, 12, 13 minutes? Great. This is a great time, I guess. Thanks for your presentation. It's neat. It's you focused on what you wanted to focus. So that's great. Let's see. Just maybe some questions to take the remaining 6 or 7 minutes. Would be great, I guess. So. Yeah. So the first question, I mean, you presented the ideal situation. This is like a very simple question. How do you choose the ideal, R, C values and so on and so forth? Was there any way to actually do that? So like, you explain that, whoever wants.
Now we actually make some exercises with teacher Eric, like this week and the last week, and we took those parameters, well, those values for R and C, from an exercises, but we also compared with a classmate that she really did the capacitor like a more professional way. She did it here in the laboratory.
Who, sorry?
Anna Ceci. Is one partner, one classmate from the.
From.
Yes,
from
we
Notre-
compared the values we
Okay.
choose from the presentation with
Great.
her values, and they were like similar. Because what we noticed is that the resistance has to be higher than the capacitance,
Great.
and that's why we choose those values, because they were a better representation of what we wanted to analyze in this challenge.
Great. So that's like to resume everything. Sorry, to summarize everything. Like, so there's particular values you chose so you can show a better way to actually simulate what you can actually construct by your own hands. That's basically what.
Yes, because
Great.
you actually saw it
Yeah.
when we did the capacitor,
Yeah.
and it was like pretty useless because we didn't obtain any charge from the capacitor, from the capacitor,
Right.
and it's the sorry.
and in a long
Don't
time.
you worry.
Yes, it took a long time for the capacitor to charge, but it didn't charge enough to let us to have any measurement on any parameters to analyze. So actually, the charge with respect to time and the current with respect to time with our experimental values was 0, because it was a very small number elevated to a million number. It was a pretty small number. So actually, that one of the opportunity areas that Mish mentioned was that MATLAB didn't recognize that values and it didn't plot them. So we couldn't analyze the circuit with our experimental values because they were too small.
Thanks, Fred. Maybe I want some of the other guys to elaborate on maybe for the situation. So what's great about the project, I'll say, or at least the presentation, is that you said like the full computations of everything, which is not expected, which is great. It's like a laboratory report or something, which is not expected for me at least, which is great. But so the question is, if you saw on your computations, on your simulations, that you were not about to get the expected values for capacitance, at least you could have a measurement for. So the question is, didn't you try, or why didn't you try like a second time for a better construction of your capacitor? You can actually have a measurement, like a real measurement. You have any particular situation on that? Whoever wants to address this, would be great.
We run out of time.
Yeah,
Yeah.
actually, well, in the experiment, as my classmate Romero said, we did 2 experiments.
Yep.
The area, well, the only difference was that in the second experiment, the area was the double. So at the time we took the measures of the difference of the charge of both plates, we noticed that the difference of the previous value was like very low. That's why in the second, well, we didn't even put it in count because it's now were not considerable. And indeed, like honestly, we ran out of time. We would love to make a more complex, more
Efficient.
professional and efficient experiment, but indeed we weren't able to because of time, because, well, doing all of the development of the challenge, and well, that was the main reason.
Okay, I mean, it's a great way. You can actually take your real values and simulate them, and then take some like potentially real values, let's say, and then simulate them, so you can actually go to. I think that's great that you have presented that. So maybe about regarding the supercapacitors research part of it, you like very briefly mentioned about this situation. Can you elaborate a bit more on your research on supercapacitors? I mean, are there any either materials that you investigated or any circuit arrays, I mean arrangements that you can actually make? Can you please elaborate on any of this? Any of the remaining guys haven't answered yet?
Yeah, we discussed with the team
Yep.
that to have a supercapacitor and we have more efficient, we discussed that the materials that we use were very important, and the environment also is important, and what else? The uses of professional materials also they're important, and what else?
Well, for a capacitor, they always, we make a research and they use materials which have a really high conductivity. But I think the better way to find the material we want to have for a really great supercapacitor, it could be making experimental with different programs, but like MATLAB, graphic, all our data, so we can find the better material, the distance we want to have between the plates, and also, the area they have, because, the capacitor and the capacitance depends only on the distance and the area, the geometrically of the plates.
Don't you worry, it's just a reference, but thanks for answering the question. I don't know, maybe just one final question. In your comparison between Euler's and Runge-Kuta's method, you presented like a comparison of the two methods. One it was like not like two previous, like this one.
Yeah.
Yeah, I mean, I wasn't sure if this is the same simulation, because that's what I understood. What's the main difference? I mean, because you have like a different maximum charge in both of them, right? I don't know, but you mentioned that this was the same simulation, so I'm not sure that's actually the same, because you have like double on the right hand side and on the left hand side. But yeah, that was like something that came to mind. I don't know if anyone wants to comment, but for Alberto, I don't know if you can comment on this, or
Yes.
yeah, that'd be great.
Yes, that's because the ODE method, it rises exponentially. As you can see, it rises much. It have a bigger increment at the beginning than the Euler's method. And if you take away sum, it consequently rise to this value. But the main difference between those is that this rises in a
Quicker way? That's
in a
it?
bigger way. Yeah, that's it.
So
Because
just follow-up questions. So if you let this left-hand side simulation go through, so it'll take the same top value, I'll say the same limit value?
Yes, but it takes more. As you can see, it rises this value in time t, and here's time t, and it hasn't reached.
Yeah, that's what I'm trying to do. Never mind. I'll say,
Sorry, I think that I don't know if it was a mistake from the code,
yeah.
but it actually in the y-axis this starts from 4.5 and this from 9, so there might be like a difference between these two graphs, because
Correct.
this is like coming like here and much closer. So what Alberto said is
Yeah.
that if you sum out this graph, that might
Probably.
look, it's supposed to look like this one, like tending to 0 in a certain time. And so I think that is the mistake in these graphs, that
Okay.
the
Fair enough.
y-axis is different.
Fair enough. That's great. Thanks very much, guys. I think that's it. So, guys, would you mind just stepping just 1 minute outside?